Okay, so your last video officially from me. I might have said the last one's the last one, but I might have lied, and this one is the last one. This is going to teach you how to name alcohols, carboxylic acids, and esters, the three organic compounds we're going to be using in the esters lab. So the naming goes the same for all three of these different types of organic compounds. The functional group appears on the longest carbon chain. Whichever carbon is closest to the functional group gets numbered carbon number 1. Branches are identified the exact same way. The carbon is counted so the branches appear on the lowest numbered carbons. And we're going to start with carboxylic acids. Hopefully you remember from your functional group quiz that a carboxylic acid has the rest of the carbon chain on the last carbon of the chain, or the first carbon of the chain. You can flip it, remember, because molecules are three-dimensional and constantly rotating. That carbon contains a double bonded oxygen and a single bonded oxygen. Just to remind you, so when you go off to your next organic chemistry class, if you do, this carboxylic acid has a double bonded oxygen with 2 lone pairs, and this single bonded oxygen has 2 lone pairs. That's what makes these things so incredibly reactive, is these electron-rich sites. So please remember that in the future. Also, as aforementioned, we always assume that the functional group is going to be on the first carbon of the chain. So whenever I name one of these, I am going to name it by the size of the carbon chain, numbering the carbon chain from the one with the functional group. Choose my prefix that came from the list that I gave you a couple weeks ago, and then add the suffix oic acid. So how this is going to look is I'm going to number this 1, carbon 1, 2, 3, 4, 5. 5 has the prefix pent, so this is going to be a pent-anoic acid. Now, since it's a straight chain, no other particular branches, you can put an N out in front, but it's not necessary. And that's how you name a simple carboxylic acid. Let's take a look at a couple more complex examples. So here's 2 examples here. We're going to first draw a pentanoic acid, that's 2-ethyl pentanoic acid with a branch, and then we're going to name this complex chain down here. So to start off here, I'm going to draw 2-ethyl pentanoic acid. Always start with the chain that is my parent chain. It has 5 carbons. So I'm going to go 1, 2, 3, 4, 5. And this can go on the first carbon or the last carbon because I would number it number 1 regardless. Here comes my carboxylic acid. And then I'm going to number my carbons from the carbon that contains the carboxylic acid. 1, 2, 3, 4, 5. And I will notice that on the second carbon, there's an ethyl group. 1, 2. So here's my first, second carbon on my ethyl group. I need to double check that my pentanoic acid is still my longest chain. So if I count 1, 2, 3, 4, that chain also contains the carboxylic acid, but it's shorter than 5. So this is going to be the correct drawing for this particular molecule. Now we're going to name this particular molecule. I'm going to start by numbering the carbons that contain the carboxylic acid. 1, 2, 3, 4, 5. I keep on liking pentanes as examples for this. I could look for a longer carbon chain that contains the carboxylic acid, but it doesn't exist. This one would be 1, 2, 3 carbons long, 1, 2, 3 carbons long. So it's definitely still 5 carbons. And on the second carbon, I've got 2 single carbon groups, which are methyls. So remember that I go location first, 2, 2. That tells me what number carbon they're on. I'd say I've got 2 of the same size branches, so I use the prefix di. They're 1 carbon long, so I say methyl. And then my longest chain is a pent, so I say pentanoic acid. And that's how I'm going to name that particular molecule. So let's move on to alcohols. So hopefully you remember that an alcohol has the O single bonded H at the end of the rest of the carbon chain. That's what the structure looks like. And again, we are going to assume that the longest carbon chain contains the OH group, and the suffixes we are going to use is all, hence alcohol. So, naming this one, I bet it is going to be 5 carbons long, because I guess every animation I found for this is 5 carbons long. 1, 2, 3, 4, 5. This is not a carbon. This is bonded to an oxygen because there's no break in the line. So this is going to be a straight chain carbon again. So I'm going to say N. It's not a necessity, but sometimes it's nice. And I'm going to say pentanol. N-pentanol is this particular molecule. However, I'm going to change this up just a touch so I can show you what happens if the alcohol is not on an end carbon. Let's say I take this off of here and I instead move this alcohol to right here. So now my longest parent chain that contains the alcohol is 1, 2, 3 carbons long. So even though the carbon chain, the longest one, is still 5 carbons long, it does not contain the alcohol. So what I'm going to say here is that my new longest chain is a propanol. And then on the third carbon, or I'm going to renumber this, that'll be on the first carbon. On the first carbon, I've got a 1, 2 carbon chain, which is an ethyl. So I can say it's going to be 1 ethyl propanol. So even though the chain has decreased in size, since the chain has the alcohol on it, that's going to be the one that's going to be the parent chain. Here are some examples that, ironically or not, are not pentanols. Here we've got 2,3-dimethylhexanol. So hexa means 6. So I'm going to draw a carbon chain with 1, 2, 3, 4, 5, 6 carbons. And even though I'm going to put this at the end, I'm still going to call this one carbon number 1. And that's because it's the one closest to the hydroxyl group. So then I can number the rest of the carbons. And then on the second carbon, I've got a methyl group. So I'm going to go boop like that. And on the third carbon, I got a methyl group. So I'm going to go boop like that. And there's my drawing for 2,3-dimethylhexanol. And then I'm going to look here, and the trick is for this particular one is to look for the longest carbon chain that contains this alcohol. I'm going to see if I can find it by going 1, 2, 3, 4, 5, 6. And I think that's going to be my longest, because if I go 1, 2, 3, that's not going to be my longest. And that has to be it. And then I'll notice that on the first carbon, I will have a methyl and an ethyl group, a 1 carbon chain and a 2 carbon chain. So I'm going to now call this 1 methyl, 2 ethyl, and it's going to be a hexanol. Now, I told a few of you in class that if you were a really persnickety IUPAC person, it should be 2-ethyl 1-methylhexanol because then it would be alphabetized. But that is just too type A for my personality. So I'm just going to go 1-methyl 2-ethyl. If you do it the other way, that's still equally correct. So that is how to name alcohols. Here comes the fun part. Here comes esters. Esters, remember, have 2 carbon chains attached to them because these oxygens are actually embedded inside of a carbon chain. So you've got R for the first rest of the carbon chain, and you have R prime, which is the second rest of the carbon chain, because these esters are parked in the center. Before we get into naming esters, we first want to talk about why esters are so important. Esters are really simple to create because they're a combination of common alcohols and common carboxylic acids. We can build all sorts of molecules from alcohols and carboxylic acids. Short chain esters, like the ones you're going to use in the ester lab, are known for their strong smells. Some of those smells are good, some of those smells are not so good. All of the smells that are going to happen in the ester lab should be good smells unless you screw up. Long esters are an excellent polymer. So long esters can be used to make a variety of different materials, kind of like polyester. That's why we get the term polyester, is because we've got a chain of esters that have made that fabric. Also, nylons are made from polyesters that also contain aminamides, acrylics, etc. So this particular molecule is pretty much responsible for the modern fashion industry. So this is going to be the most simplistic version of explaining how this reaction works that I'm willing to give you right now for the last 4 days of IB chemistry. So I'm going to show you the mechanism of adding ethanoic acid, which contains 2 carbons in a carboxylic acid, to propanol, which contains 3 carbons and an alcohol group. You see that there's an H and an OH circled here. The simple fact is that when undergoing an acid catalyst, the acid catalyst is going to prompt this H to bond to this OH to make water. And when these two go off and make water on their own, the remaining 2 chains bump together to make an ester. So basically what you're going to see is the double bonded side of the ester. Oops, let me try that again. The double bonded side of the ester is going to be right here. And the single bonded side of the ester is going to be the rest of the alcohol, which is going to be right here. And they're just going to pair together just like 2 trains bond together before they roll down the highway or the train tracks and create propyl ethanoate in this case. To name this thing, what we have to remember is that the single bonded oxygen side, which in this case would be the propyl side, will get the suffix -il, YL, and the side of the chain, which the double bonded oxygen side, is going to get the suffix -08. So you actually have 2 carbon chains to name here. So here's a couple of examples. Whenever I see an ester, and I know it's going to be an ester because the last word, the suffix is -08, whenever I see that, I'm going to start by drawing the longest carbon chain that goes with that. So propanoate is going to be 1, 2, 3 carbons long, and it's going to have since it has the O8 at the end, the one with the double bonded oxygen. Then what I'm going to do here is I'm going to realize I'm going to go to this second part with the ill at the end, and I'll notice that there's two of them. The first one is going to tell me the size of the chain with the single bonded oxygen. So I'm going to first draw my single bonded oxygen, and it's going to have 4 carbons because the prefix butyl means 4. So I'm going to go 1, 2, 3, 4. Lastly, counting from where the single bonded oxygen is, 1, 2, 3, 4, there's going to be a methyl group. So on that side there's going to be a methyl. So I'm going to put a single bonded oxygen there like that. And that is going to be a correct drawing for butyl. That's going to be this piece here. 2-methyl, which is this piece here. Propanoate, which is this piece here. Then we're going to name this particular compound down below here, and I'm going to start with the side with the double bonded oxygen. So I'm going to number this 1, 2, 3. I could also number this 1, 2, 3, but that's going to be absolutely identical. And so when I see here that I've got my longest chain that contains the carbonyl or double oxygen group is going to be 3 long. It's going to be a propanoate, just like above. And then what I'm going to see here is on the second carbon that I am going to have a methyl group with 1 carbon. So this one's going to be a 2-methyl propanoate. And notice I put those together because I need to let you know that the methyl group is on the double bonded oxygen side of the double bonded oxygen, or the carbonyl group. And then the last thing I'm going to do is look at my alcohol side, my single bonded oxygen side, which I'm going to go 1, 2. The size of that chain is 2. And so what I'm going to say here is it's going to be an ethyl. So the IUPAC name for this particular molecule is going to be ethyl 2-methyl propanoate. You will learn later on, if you take an organic chemistry class, when you have a methyl group in the middle of a propanone, a lot of time this is called an iso group. And I can also name this particular organic compound ethyl isopropanoate. And that's just when I have a secondary carbon attached to a carbonyl group double bonded oxygen. So your task for the Esters lab is as follows. You are going to get a series of alcohols, get a series of carboxylic acids. You're going to mix them together with an acid catalyst, and you're going to create an ester. You're going to write the formula and the name of the alcohol, the formula and the name of the carboxylic acid, the formula and the name of the ester. And then hopefully maybe if you do this right, you can predict the correct smells that over time have been paired with these particular esters. So hopefully this was helpful. Let me know if you have any questions. There's no worksheet that goes along with this. This is just to prepare you to finish up your last assignment of IB chemistry for your senior year. Have a wonderful day. Thank you for making it through all of the videos I ever made for you. Have a great day.